Hello everyone, welcome back. We started going through the procedure of how to solve a problem in gas dynamics, 1D isentropic gas dynamics through a convergent divergent nozzle. I discussed how to solve when it is a simple case of isentropic subsonic flow fully. I do not want to go through that. I believe you can solve it by yourself. Okay, all you need to do is A by A star calculations. Now a better one to do will be a case where it is non-isentropic somewhere in the middle. Even if it is subsonic here, becoming sonic and going supersonic all through here, we know that A star is this value and I am given area at every point. I know A by A star everywhere, which means I can solve this problem immediately. If it is fully isentropic problem, I just have to go to isentropic tables. A by A star will give me that particular Mach number. It will tell me the P by P naught. I know the P naught, so I can get pressure here, T by T naught, so I will get temperature here, whatever, any location, even if it is here. Only thing you need to think about is, given A by A star, am I having a fully supersonic flow or a fully subsonic flow in the divergent portion? Depending on that, I will have either, am I going to go past, if I plot P by P naught 1 versus distance, I could have a curve that is going like this. This will mean I am using A by A star going subsonic solution. If it goes like this, I am using A by A star going supersonic solution. These are easy problems to solve, and you know that this is going to reach up to P critical 1 by P naught 1, P critical 3 by P naught 1, and if there is a shock at the exit, then I get P critical 2 by P naught 1. And P naught is somewhere there. That is your P naught, P equal to P naught, so it is P by P naught equal to 1, that particular condition. These are the cases. If I have to solve a problem along this particular line, then I know that my throat is choked, then I will say that is my A star. I know area everywhere in my nozzle, then only I can calculate flow inside the nozzle. So A by A star, I know I will get subsonic here, subsonic Mach number. On this side, if I am going over this particular curve, then I will use A by A star and get subsonic Mach number. Once I know the Mach number, I can get pressure, temperature, any other property I want. If I assume that it is coming here sonic and then going supersonic all the way till the end, then I am going through this particular line. If that is the case, then I have to use A by A star. A by A throat will become A by A star for you because throat is choked. After that, all I have to do is find the supersonic solution for that particular A by A star at that location, and then you can solve the problem from there. Once I know the Mach number at the location, isentropic flow tables, I will get P by P naught, T by T naught, whatever else you want can be obtained once you get pressure, temperature. So I can do everything here. A more critical problem to solve will be the case where when I am in between these, in between critical pressure 1 and critical pressure 3. So we will pick up that particular example today and start solving the problem. Okay. So I have picked a particular nozzle where I am going to say I am starting with A by A throat equal to 3 and ending with also A by A throat equal to 3. I am not telling anything about whether the throat is choked or not. I am just telling A by A throat is this. It may be that my pressure at the exit is very low, very close to P naught, and I am not even below P critical 1, in which case my pressure distribution will be more like this. If it is something like this, then my throat is not choked. That could be a case, which is what we dealt with last class towards the end. So in today's class, we will just assume we are going to go in between critical pressure 1 and critical pressure 2 and we want to solve the problem. We will just pick up that particular case. So I am going to assume gamma equal to 1.4 for this problem. I am going to say there is some Pb back pressure and some P naught 1, and since we already discussed that if I want to change Pb by P naught 1 ratio, I could either decrease Pb or increase P naught 1. We will not worry about what experiment really I am doing. All I will worry about is I am getting a particular ratio Pb by P naught 1. I will just work with that for now. Okay, that should be enough to do stuff. Okay. So I do not know what pressure I should use for this particular set of ratios of A by areas. So what I am going to do is first find the critical values PC1, PC2, PC3. How will I find PC1? P by P naught 1, critical 1. How will I find that? I am going to assume that this is getting choked here, and then I am going to have subsonic flow all through till here, which means this A throat becomes my A star, right? It is choked, which means now I can use this A by A throat as A by A star at this location. So what I will do is, I will go and find A by A star equal to 3 subsonic solution. That will give me a Mach number from my gas tables or compressible flow tables, isentropic flow tables. I am going to get to a value 0.197, and I am going to approximate it to 0.20 because my tables have only accuracy up to 2 decimals in my Mach number. I wanted to interpolate, but then I found it's too difficult. I will just use 2 decimal accuracy. Okay. Now I have to go and find P by P naught for that Mach number. Since the whole flow is subsonic in my P critical 1 condition, all are subsonic, completely isentropic flow, I can just go use isentropic tables at m equal to 0.197. That is going to give me a value 0.973. So that becomes my first critical pressure ratio. Okay, this is my first critical pressure ratio, and how I got it is here, just next to it. Okay, this is how I got to this point. Now I have to do next thing, P critical 2. It is easier to go to P critical 3 and then come to P critical 2. So I will directly jump to PC3. You will know why, or the way we solve it you will know immediately. So what do we do in critical pressure 3? I am going to say my pressure is going to decrease continuously all the way to supersonic solution up to here, which means subsonic solution became sonic at the throat and became supersonic continuously. So now I can again say that my A throat is my A star, and A by A throat is equal to 3 will now become A by A star equal to 3, but my flow is supersonic here. So I just have to go and use A by A star equal to 3 supersonic solution, and go look up tables, and you will get a Mach number of 2.64. Okay, and corresponding P by P0 for that Mach number 2.64 is 0.047. Okay, so I will just write that number here because that will be the pressure ratio if I am having perfectly expanded supersonic flow in that nozzle, in this given nozzle. Remember that this is for this particular nozzle with A by A throat of 3, it will not be working always. Okay. By the way, what will be the Mach number here at the inlet of my duct? You have the answer on the board, by the way. It should be equivalent to A by A star of 3 subsonic solution 0.2, that is what it should be, right. When I am in this condition, it is going to be 0.2. Even when I am at critical 1, it is also going to be 0.2. It goes from 0.2 to 1 and then decreases back to 0.2 if it is critical pressure 1. Otherwise, it is going to go from 0.2 to 1, and from 1 it is going to go increase to 2.64 at the exit, okay, depending on the conditions. If I want to find any intermediate condition, what should I do? Find that area, whatever be the area. Let us say this is 3, right. Let us say this is A by A star of A by A throat of say 1.5. Then all I have to do is, since I know it is choked at the throat, A by A star is equal to A by A throat, that is 1.5. Go to isentropic tables, find the Mach number, find the pressure ratios, find the temperature ratios, get multiplied with P naught or T naught, you get to the answer. So I won't go through the details of it here, but the next problem I am going to solve the full thing, where you will go through this detail also. We will go look at that case anyways. I still haven't gone to the full problem. Critical pressure 3 I have to mark, sorry 2, we have done 3 already. Critical pressure 2 with P naught 1, that ratio. How will I get it? I am going to say it is going fully supersonic up to the exit. At the exit there is a normal shock with that particular supersonic Mach number, and then immediately after that PB is matching P exit. That is my critical pressure 2. For that to happen, I should have a Mach number 2.64 at the exit, and there should be a shock at that Mach number. So all I have to do is M shock equal to 2.64. I already did P critical 3. That is why I did this before the other one, P critical 2. Okay. So once I have done that, now I just have to find from here P2 by P1 at M equal to 2.64. If I find this number, that happens to be 7.965. This is all for gamma equal to 1.4 I am solving. Okay, I am getting this particular number 7.965, and if I have to find the exit pressure now after the shock, what will it be? I will take the previous exit pressure, which is this value 0.047 into P naught, multiply it with P2 by P1, that will give me my aftershock pressure. So I am going to multiply these two, and that will be my new exit after the shock. If I multiply this with this 0.47 multiplied with 7.965, I am going to get a number 0.375. That is my critical pressure 2. Okay, these are my numbers. This is what I am having. Critical pressure 1 is 0.973, critical pressure 2 is 0.375, critical pressure 3 is 0.047. This is what you are having. It is easier to calculate 3 before 2 because 3 is needed for 2. Okay. So we will typically use this particular order in calculating nozzle flow problems. Okay. We haven't actually started our problem. I wanted to solve a problem where there is a shock sitting in the divergent portion. Now we know what should be the pressure. Pressure should be the pressure at the back pressure to P01 ratio should be somewhere between P critical 1 and P critical 2. Okay, 0.973 and 0.375, in between these numbers. Okay, and just for the fun of it, I picked the number 0.5. Simple enough, it is definitely in between those two. Okay, and now we want to solve this problem, and all we know as of now is there is a shock definitely in the divergence portion, right? From all our discussions last 2 classes and the experimental video we saw, we know that definitely there is a shock in the divergent portion. Okay, now we will say that we want to find the location of the shock. Okay, I am not interested in finding the exact x location or the axial location. All I care about is the area at which the shock is standing. Once I know the area, I can just go and look at the geometry of my nozzle and tell where that area occurs in my duct. So we will worry about area at the shock location, that is all. Okay, we want to find that. The only way we can find this happens to be by guesswork. Okay, because unless I put a shock at a particular place, I cannot tell what will be the pressure downstream, and I have to solve the whole thing from left to right all the time. Okay, if I am doing that, I cannot tell what this will be unless I know this. So how will I think about matching the pressure here? I will have to adjust this way till that pressure matches the back pressure. Back pressure is given to be 0.5 already, 0.5 of P01. Okay, so I have to keep adjusting this till I get to the correct pressure. This automatically calls for iterative procedure. I have to go through iterations. Okay, let us say I guess my A by A star for shock to be 1.5, just a guess. Okay, because it should be somewhere between 1 and 3. Okay, because 1 means throat, 3 means the exit. Okay, it should be somewhere in the middle. I picked roughly half. Okay, so I go and use my supersonic A by A star value to find what will be the supersonic Mach number. I am going to call it M1 shock. At the shock, the Mach number just before the shock, that value, that happens to be 1.86. Now I go to normal shock tables at this point, take this number, go to normal shock tables, and that is going to give me M2 shock as 0.603 and P02 by P01 is 0.786. Okay, there are so many ways of solving it. I track only P0 because once I track P0, if I know Mach number, using that P0 and Mach number, I can go to isentropic tables and calculate my pressure at the exit. I am going to use that method now. Okay. I could of course do pressure ratios P2 by P1 and then tell that the Mach number based pressure ratios P2 at previous area to pressure at previous area to pressure at new area, that ratio can also be found. That is too much work. This is simpler. This is the shortest route, I think. Okay. Once I have this number, now I am actually located, I will just draw the picture here, it is easier. I am somewhere here, I am currently located at this point, okay, because I have calculated every property that I need. We know the T naught also, by the way, T naught 2 by T naught 1 is 1 in a shock. So I know every property at this location now, I have crossed the shock. Now I know that the solution here is subsonic, m less than 1. I have to go all the way to this exit whereby A by A star is equal to 3. Oh wait, be careful. A by A star 1 is equal to 3. Why? Since my P naught dropped, my A star would have increased. Okay? That is where you have to think about again. I know my P naught has dropped to roughly 78% of the previous value, which means for the same mass flow rate to go through, I know my function looks something like this. Function of gas is not changing, so we won't worry about it. My T naught does not change across a normal shock. P naught and A star. Now I know my A star dropped. Okay? Sorry, A star increased. P naught dropped and A star increased. To keep the same mass flow rate, that has to happen. Okay? So now we have to work through the whole thing again. Okay? There are several ways of working through it. I can of course find the new A star just from this relation. Okay? Just from this relation, I can find my new A star with respect to old A star. How can I do that? A2 star by A1 star is equal to P naught 1 by P naught 2. I can use this also to maintain same mass flow rate. This has to be true. Okay? I can use this, or I use something much more simple because I just go to direct tables and just look up numbers. Okay? I know my Mach number at that section. Okay? Once I know the Mach number at this section, I can go and find A by A star corresponding to this value. Okay? I will go do that. From here I go to isentropic tables and I will find A by A star. Now I will call it A star 2 because this won't match your previous A by A star. If I find this number, that number happens to be 1.188. Okay? Does this prove that my A2 star increased? A2 star is higher than A1 star? Can you say that? Yes, you can. Why? Previous A by A star which we started with was 1.5 at the same location. We haven't moved yet. It is the same location. Okay? That says that across the shock, this is my A1 star really. Okay? A2 star is lesser. A2 star is higher, the denominator is higher, so my ratio is lower. I have gone to this point. Now the same A star will go from here all the way to here because the flow is isentropic here. Nothing is changing. Same mass flow rate, isentropic. So it has to be the same. So now I can use the same A star. I have to find the A by A star at the exit, which is what is our goal. We want to match that with 0.5 of P naught 1. That is the goal for us. So how will I find that? I have to find A by A star at the exit. How will I do that? What I actually have to do is A at x by A star 1. I know, because this is what I guessed. I guessed it to be 1.5 and I am going to 3 from there. Okay. So similarly I have to work through the numbers. Okay. So how will I find that? If this is 1.5, that will be 3. If this is some other value, I have to work through that again. Okay. So what will that number be? This is going to tell me my A exit by A star 2 is going to be 3 by 1.5 into 1.188, right. So let us find this number. That is going to be 2.376. Okay. Once I know this, I know A by A star at the exit, and I know the flow is subsonic at the exit. So all I have to do is go look up A by A star in subsonic tables, isentropic, find the subsonic solution for Mach number at the exit. So that is going to give me a Mach number. I will put an approximately equal to sign here because the numbers are not exact. I did not want to interpolate. Okay, it is close to that. It is 0.26 roughly. So this is going to tell me that my P exit by P naught 2, this is what my Mach number isentropic tables will give. That number P exit by P naught 2 happens to be 0.954. This is what it comes out to be. Okay. So what will be my P exit by P naught 1? How will I find that? Multiply this one with P02 by P01. Okay. I have to multiply this and this, then I will get, this is a standard thing, no, ratios being multiplied, that is gas dynamics people, we always love it. So it is going to be 0.954 into that number 0.786. That is going to give me a value 0.75. Okay. If my shock happens to be at A by A star of 1.5, then I am going to have an exit pressure of 0.75. But what was our target? 0.5. I did not meet it. Okay. So what should I do? What should be my next guess for my A of shock? Where is the shock going to located? What should be my next guess? Area higher, area lesser? Area higher, why? We have to decrease the pressure at the exit. Expansion fans will come in, weaken the shock will be thrown more out. That is one way of looking at it. If you do not like the explanation, let us go to the screen. Okay. We will go to the screen. Oops. Okay. All I have to do is just remember that as the shock goes downstream, the pressure at the exit drops. This is the only thing you need to remember. If you remember this, then things are easy for you automatically. Okay. I did not want to choose this exact nozzle because you can just use this plot and give me answers. I picked a nozzle with exit area as A by A star of 3. This happens to be 10. Okay. I just picked some other case. Okay. So all we know is if I want to decrease the exit pressure, my shock has to go more downstream. Okay. Now we will go back here. Since it is an iterative process, you have to go over a particular table. I will call it A shock, I think. A by A star shock. Okay. M1 of shock, M2 of shock, P02 by P01, A shock by A2 star, A exit by A2 star, M exit, P exit by P02, P exit by P01. These are the things you need to calculate in this sequence so that you will get to the answer. So I will just write whatever we just calculated in this table for the first round. 1.5, 1.86, 0.603, 0.786, 1.188, 2.376, 0.26, 0.954, 0.75. Okay. Now after this, I know I made a mistake in my calculations. So anybody has gas tables here? No? Okay. So you are going to be my gas tables and calculator. Okay, it has gas tables at the end. I know I made a mistake there because I did not change the areas accordingly. So we know that I have to guess a higher area. So let's guess an area 2.0. If I guess an area 2.0, I am going to use A by A star of 2.0 and get a supersonic solution. That is going to be 2.2. Okay, and if I go to normal shock tables, that's going to give me 0.547. Okay, and if I go look at the same normal shock tables, I will get P02 by P01 of 0.628. Okay. After this, I have to go and use this number M2 of shock to go and find my A by A star. Okay. If I use that, I am getting a number 1.26. Now I have to find from here A exit. Okay. Now you guys need to calculate and tell me for that. 1.26 multiplied by 3 divided by 2. 3 is the exit area, 2 is the actual area which we guessed. Okay, 1.5 times this, right? 1.89. Okay, from now on I want people to tell me numbers. 1.89 A by A star, I want to find my Mach number from there, subsonic Mach number. What is that? 0.39. 33. Now for this Mach number I want P by P naught. Same row, I just have to look at numbers. If you have the reciprocal, just tell me the reciprocal will invert. Or tell me the actual value. .918. Okay. Now I have to multiply the 0.918 with my P02 by P01, 0.628. Multiply this with this. What will be the number? 0.5? 0.577. That's fine. 577. 3 decimals is probably too accurate. It may not be that accurate when we calculate stuff. Okay. 2 decimals are really enough. Okay. So yes, we have moved in the correct direction. When we increase area, you are finding that the exit pressure has dropped. You have to decrease it a little more. I don't know how much to decrease. Let's guess 2.3. Okay. Yeah, we'll guess 2.3 right now. Okay. So if my A by A star is 2.3, what should be my Mach number? So I am looking for tables. 2.36. Now we go to normal shock tables. 2.36. I want the downstream Mach number and P02 by P01. 0.527 and the P02 by P01. 557. Okay. With this Mach number in isentropic tables, now I want A by A star. 0.527 A by A star for that. .32. Okay. Now I have 1.32. I have to make it 3 from 2.3. So into 3 divided by 2.3, I want that number. .72. Okay. Now we go back to isentropic tables. A by A star giving Mach number. 0.38, and for that condition I want P by P naught. 0.905, that multiplied with 0.557. So next number. Okay, you guys understanding the procedure? That's the same sequence we keep on going. 0.504. Okay, since this is close enough, we'll stop here. I don't want to keep spending time. You know the procedure. Okay, this is close enough to my starting condition of I want it to be 0.5 of P01. So I am getting this close. So I am going to say my shock is supposed to be sitting at 2.3. It's lucky guess for me. I could have guessed 2.5 and I would have gone a longer process. Okay, I just guessed close enough. If I guessed 2.29, I would have hit it exactly. Okay, it's just close enough for us. Okay. Anyways, but remember that you have to convert the areas accordingly. This is the mistake I made in my notes, and that's why you are doing the calculations now. Okay. I realized it while I was talking about it to you guys here. So you are prone to make so many mistakes here because you have to look at different tables, and if you have a full compressible flows tables, you will have different gammas tables. Sometimes you will use gamma equal to 1.67, sometimes you will use gamma equal to 1.4. Ideally you have to use the same table all the time, and then you have to use isentropic tables, normal shock tables. Okay, so there is so much of confusion possible. Okay, and instead of subsonic you will use supersonic, things can go wrong. Okay, so you have to be very, very careful. You have to be more alert, mentally prepared for doing this problem. So we will do more exercises. I will put up some exercises on the web anyways. Okay, so it's just practice. Now of course you can always go and tell I don't want to hit 0.5 but I want to hit 0.25. There's a problem if it is 0.25, is it? If it is 0.25, I am in over expanded regime. Remember, it's below P critical 2. I cannot use 0.25. So choose say 0.6 and solve the problem again. Okay, if I choose 0.6 and I want to solve the problem again, new problem, P exit by P0 should be 0.26. 0.60. If I want to do, I have the first two columns already ready for you. I know the answer is in between these two and very close to 2.0. Okay, so I'll guess something like 1.95 and that may hit the answer immediately. Okay, but you have to do that one more column, the one more row of the same thing. This is the procedure used in general, and that is exactly what I use to get this whole plots which I am showing all this time. Okay, there's a computer program which is doing this exact procedure. Okay, that's the way you have to do. In fact, it's a good thing if you go and write your own code to solve this problem. Okay, then you will understand the details of it. After some time you will be comfortable with gas dynamics problem solving. Okay, it's fun to solve these. Now we'll assume that you know how to solve any problem in convergent divergent nozzle. Is there any other questions you have which you may not know how to solve? The only thing I have left out happens to be the remaining cases. We have solved a problem P01 to P critical 1 last class, not with numbers but with just ideas. This class we did problem from P critical 1 to P critical 2, and at P critical 3 we have solved. Only cases which we haven't solved are region from P critical 2 to P critical 3 and below P critical 3. It so happens that for all those cases inside the duct it is exactly the same pressure profile. So I will solve the same thing as P critical 3 and it will be the same everywhere inside the duct. Ideally the remaining portions over expanded and under expanded I had to talk after I introduce jets to you guys, because only outside the nozzle things will change. Inside the nozzle it's exactly the same as critical pressure 3 condition. Okay, if you know that, you know how to solve the problem now. Okay, now I will give a more complex problem. Double throat nozzle. I am having one convergent divergent nozzle and it is having a small bump here and then it is going like this. Let us say I have a nozzle like this and I want to solve the problem in this. Okay, and let us say the other side is just straight, does not matter, I am just worrying about area variation because it is 1D problem analysis anyways. If I pick such a problem, there are two throats, we know that it is going to choke at minimum area as long as I am giving enough pressure difference across it. Let us assume I am giving enough pressure difference that it is choked at this condition, otherwise there is no fun in this problem. Okay, we will consider a case where there is some little fun in this problem. So we will consider this particular case. How will I solve this problem? if it is fully subsonic solution, I am going to say it is going to go through as A by A star. I am assuming it is choked here. If not, also you can solve the problem similar to what we talked about last class towards the end. Same procedure can be applied here. That is not interesting enough. So, we will go to a case where there is shock in the divergence section. Okay. Now, for finding the exit conditions, I will follow the exact same procedure as we followed for single throat nozzle and find the area location at which the shock should be present. Exact same procedure will work, okay, except for this small range of areas, there are multiple locations for the shock possible. Okay, that is the only special thing. If my pressure is such that the shock is supposed to be here, it will be here, there is no difference. If my pressure is such that the shock is supposed to be at this big area, it will be here, no problems, then this will not be there, no problems. What if my pressure is such that the shock is supposed to be some area here? Could it be here, here or here? Where will it be? There are 3 places. I will give them A, B, C, 3 possibilities. I have gone through the calculations and I found that the A by A star at which the shock is supposed to be located for me to satisfy the exit conditions happens to be that particular area. Now, I have 3 possibilities. The area happens to be this height, that is the area where my shock should be standing. Now, I have 3 possibilities for this. Where will it stand? Okay. Now, we have to go and think about it a little more. It so happens that shock is not, I am giving you a new information here, okay. Shock is not stable in a convergent duct, okay. Shock is not stable in a convergent duct. It can be proven and it is related to unsteady flows, we won't worry about it right now, okay. Can be easily proven, not very difficult to prove, but we won't worry about it right now. We will just say that shock is unstable in convergent duct, which means B is not a possibility. I still have A or C, both are divergent ducts, okay. Now, which one will it be? Now, it depends on history, okay, it is related to history, whatever history of the shock. If I am slowly making the shock move from here, say I am increasing P naught, keeping back pressure constant, I am going this way, from here as shock is moving continuously, then it will go and reach this point A. Till the shock goes to this area, I keep on increasing P naught, it will be sitting in this side. If it needs to go to higher area than this maximum point here, then it will jump to that point and from there it will keep on increasing area further to there, okay. In case I have pushed my shock here and I am decreasing my P naught or increasing my back pressure, whichever, then my shock will start coming back. When it comes back now, it will not jump from that location directly to this peak, it will not, it will just keep on going on this convergent, the divergent portion back this way, it will keep on going this way till it goes to this point, okay, till the shock goes to this point, and then if I decrease it any lower, P naught decreasing a little bit, it will jump to a lower area and that is only possible in this section, so it will jump to this point. That is what really happens there. Okay. Shock wants to find an area where it can sit so that it matches the exit condition pressure. That is the idea for the shock. It will find whichever is closest. So, it could be A or C. If the shock is here and it has to come to this area, it will come to C. If the shock is here, then it will go to A. What if my shock is at this peak point, at this location, and I decrease my P naught? It will still go to A, that is the closest. Okay. If I am here at this location, shock is at this point, this line, vertical line here, the minimum of the second throat, if you think about it. If it is here, if I increase my P naught only, it will go to that point. You guys see, right? It is going to a higher area, it is more downstream. If I think about simple convergent divergent nozzle, if I increase P naught, it goes downstream. So, it will go that way to reach that point. If I decrease my P naught, then it will jump to this solution somewhere here, it will not reach A. If my shock is anywhere in the second divergent portion and I reach that particular P naught, it is going to reach C. If it is in the first divergent portion and I reach that particular P naught for that area, then it will sit in A. Okay. So, it is related to history of the shock. Okay. Now, you can think about what if I oscillate up and down, then my shock will go like this up to this point, jump to that, go there, when it comes back it comes all the way till here and then jump from here directly to here. I will keep on doing this if I keep oscillating my P naught or my PB up and down across this point. Okay. That is all fun to think about. Okay. Next thing, this is a serious question which I asked long time back and we still did not answer very well. I am having a duct that is something like this. How many times can I choke a flow in a duct? That is the question. It's a single duct and I want to choke the flow as many times as I can. How many times can I choke the flow? That is the next question we want to ask. Okay. Let us say initially I did not have any of these bumps, I just had one CD nozzle and then a straight line duct. I set some pressure and I put a P naught and I know it became supersonic after this point. Okay. Or you want, I just worry about choking, it choked definitely. I went below P critical 1 for this throat, it choked. After that, if I wanted to choke again, what should I do? I wanted to choke again, in a sense I want this choking to be present and this choking to be present. What should I do? How will it choke twice? Let us not worry about thrice, 4 times, 5 times, whatever. How will it choke twice? I can choke twice. How? I believe I told this long back once, just as a passing mention, you just have to figure out when. Anyways, how will it happen? All I have to make sure is m dot equal to P naught A star by square root T naught function of gas. This is what I need to think about. Keep remembering this formula. Mass flow rate is a constant in a continuous duct. So, as long as I am thinking about this particular thing, if my P naught does not change in this whole flow, then I am assuming that my flow is either fully subsonic or fully supersonic after the first throat. If it is fully subsonic, let us say, then, and I am isentropic, I said, right, fully subsonic, isentropic, then P naught does not change, T naught never changes, A star will be exactly the same. Okay. If A star is exactly the same, I can put the same dent everywhere in my duct, how many ever times I feel like, and it will just go subsonic to sonic, subsonic, sonic, subsonic, sonic, subsonic, sonic, subsonic. I can keep on doing this forever. Okay. That is one possibility. It can happen, by the way. If you are having a supply line of gas, you have a big tank and you are having, after a long distance, some flow facility. There will be so many valves in the middle, each valve is like a constriction in the flow. Okay. I can have several chokings. Okay. That is one particular setting where the flow is completely subsonic or just sonic, no supersonic. Okay. Even if you make a small mistake, one of them will become choked and everything else will become unchoked. Right? That is a very critical situation. I have to make sure that all the areas are exactly the same. Even if one of them is slightly smaller than all the others, only that one will choke, everything else will be unchoked. Okay, it is a very special case, typically it is impossible to achieve it. Ideally I can achieve how many ever chokings I want, if it is fully subsonic and just sonic conditions are allowed. Okay. Let us think of the other case, much more easier case to think about. I am going to have a throat here, sonic, I put a star here, and then there is a shock here. Now what will happen? Flow is subsonic on this side. If I just think about this problem, flow is subsonic here and further down, I can make it choked here, that is easy to do, I can make it choked here. If I make it choked here, what should be the condition? All I have to think about is, this is some m less than 1, I want to make this also choked. What should I do? Mass flow rate should be constant. So I know my mass flow rate through the first throat, and I know there is a shock somewhere. I know exactly P naught 2 by P naught 1. I know my P naught at this local location and my m dot that has to go through this with that P naught. Based on that, I can find my A star from there. So if I make a dent in this pipe up to a point where this A star is achieved here, then this will be choked again. Again I can have subsonic or supersonic. Subsonic, I told you already that it is very, very unstable. I cannot maintain how many are subsonic solutions. Let us assume there is another shock after this. Okay, we will make it numbered P01, P02. Now I have a P03. That is a possibility. Okay. Now if I decrease my pressure further downstream, P back really low, then I can still make it choked here. For this P naught, I just look at this problem from this point on downstream. If I make my PB low enough for this particular P naught 3, then this condition may get choked, right. I just look at it as a module. All this point is all ignored. Currently I am just going to see this is the only portion that is left. I have a P naught 3 in my duct and I can choke this for a given mass flow rate. I know the mass flow rate, I know the P naught, I know the T naught, I know the gas, only A star is left. I can now make a new dent A star 3. Oh, I have to label A stars also. A star 1. Okay. So now I can have another A star. Typically, since P naught is dropping continuously, my areas will keep on increasing. Now in all this, I am doing one more thing which I am not stressing too much yet. Okay. We will see if you are noticing after more. If I have P naught 3 and I want to have a shock here, then this will become P naught 4. Now I do the same problem again. I will look at only this problem. There is a P naught. I can form a star 4. I can make it choked as long as my PB is low enough for this P naught 4. Okay. Now that is the statement I repeated 3 times now. As long as PB is low enough. Okay. So now I will go and answer my own question. I said how many times can you choke a duct, flow through a duct. Okay. One situation is for a particular P naught and P back, flow is fully subsonic, only some points it is sonic, then it can be any number of times. But if you make any small mistake, only one of them will be there. It is very unstable. Typically it is impossible to achieve practical situations. Okay. So we will think about the other case where there is a shock. Now it is very stable. Okay. Shock in divergent portion, very stable. Okay. So now if this is the case, as long as my PB is very, very low and my P naught 1 is pretty high, I can go to a point where I can choke it how many ever times I feel like, as long as I maintain my mass flow rate constant. Okay. Of course you should know that there is only one particular value at which this will choke. Okay. There is particular values, it cannot work for all conditions. My area should be more than at least a minimum value. If my A3 star is anything less than whatever value we get from here, then only that will be choked. This previous one will get unchoked, this one may still be choked, I do not know, that depends on the P naught value. Okay. So much dependent on P naught. Okay. Now I will give you a complicated exercise like this also, okay, so that you can have a feel for this. In all this discussion, I have assumed that there is no friction in the duct. Okay. In real life, if there is friction in the duct, there will be P naught loss because of friction also, because flow has to do work against friction. So my flow energy, the pressure energy is decreasing. Okay. If my pressure energy is decreasing, then it cannot go through that small area, it may need more area. There will be a point where that area will be equal to the duct area, and even the duct will get choked. That will be your limit. So it cannot be infinite numbers, there will be a specific number for a given P01. That can also happen. Okay. So typically you can choke flow 5 or 6 times, but it could be infinity if you assume friction. Okay. That is where you will be. I think I have discussed reasonably enough convergent divergent ducts and multiple convergent divergent portions. Now the next thing we need to go is what happens just outside the exit of the nozzle. That is your jet problem now. From now on we will assume we are having a supersonic jet exiting. Subsonic jet is no fun. Fluid mechanics people would have taught you enough. There will be a shear layer formed, and if there is inviscid flow, it is just a straight line jet going. There is no fun in it. Okay? We are in inviscid world, so we will go supersonic because there is some more fun involved there. We will consider supersonic jets into stationary quiescent atmosphere. That will be the next class. Okay? See you people next class.